day, everyone.
Okay.
Relations using chaos theory. Everyone. Good day, everyone. Have you ever wondered why a raindrop falls in a perfect sphere? Or why systems in nature moves in such complex yet patterned ways? Or why daisies blooms in such mathematical arrangements? In the book Nature's Number, with the topic Drops Dynamics Daisies by Ian Stewart, takes us on a journey to discover the mathematics hidden in everyday wonders. Let's go over to our first topic, which is drops, to be discussed by Jane.
So a lot of you might be thinking, drops? What's so special about a drop of water? Well, to answer your question, a lot actually. A drop of water may look so simple to the naked eye, but once we actually observe it, just like what the book says, it is actually very busy. Although a very common phenomenon, there is only one correct drawing of the shape of a drop, which was made over a century ago already by a physicist named Lord Rayleigh. However, in 1990, mathematician Howell Peregrine and his colleagues in Princeton University were able to photograph the process, leading to the conclusion that a drop of water is not only complicated, but also very interesting. A fluid drop hanging from a surface starts as a bulge, then it develops a narrow waist and a teardrop shape. However, instead of pinching off, this waist develops into a long, thin cylindrical thread with a near spherical-like drop at its end. This thread narrows at the point where it meets the sphere, creating a shape like a knitting needle that is just touching an orange. After the spherical drop falls, the remaining thread of fluid rounds off at its end, and tiny waves travel back up the needle towards the root, making it seem like a string of pearls that gets tinier and tinier. Finally, the top end of the thread narrows at the point, and lastly, it detaches. Amazing, right? Now let's move on to our second topic, which is dynamics, to be discussed by RD.
Why do populations like rabbits, foxes, and grass rise and fall the way they do? For years, scientists tried to explain it, using neat equations like Newton's law, only for biology. But nature isn't that simple. Real life is messy. Some rabbits have more babies than some foxes starve, and sometimes there's just a rock in the way. In 1994, three researchers, Jacqueline McLeod, David Rand, and Howard Wilson, tried something new instead of equations. They built a kind of like computer game. Picture a grid on a screen. Green squares for grass, gray for rabbits, red for foxes, and black for rocks. Then add some rules. Rabbits eat grass, foxes eat rabbits, rabbits reproduce, and foxes starve if they don't eat. Step by step, move by move, an artificial ecology comes alive. At first glance, the system looked like it was all randomness. On a huge scale, it was just averages. But then came the surprise. On an intermediate scale, patterns began to emerge. When they analyzed rabbit populations using chaos theory, they found that 94% of the changes could actually be explained by a simple model with just 4 variables. Only 6% was pure randomness. The lesson? Even in the messy, unpredictable world of ecology, order can emerge from chaos. Complex systems can sometimes be captured by surprisingly simple rules. Now let us move on to daisies, which will be discussed by Sophia.
Have you ever wondered why some flowers have petals like 3, 5, 8, or 13? These are just random numbers. These are Fibonacci numbers. These Fibonacci numbers are mathematical sequence where each number is the sum of the two numbers before it. Many biologists say it's all in the genes, but this doesn't explain why these numbers appear again and again, just like in pine cones, pineapples, and petals. In a sunflower, seed spirals comes in pairs like Fibonacci numbers. There are 34 and 55. Pineapples, 8 rows, sloping one away, 13 and the other. These patterns emerge not because they're programmed, but because of how plants grow. At the tip of a growing plant, new structures called primordia form one by one, spiraling outward, formed by one. Their spaced special angle of 137.5 degrees, the golden angle derived from the golden ratio. This angle spaces new growth most efficiently, preventing overlap and maximizing exposure. The result? Spirals that naturally produce Fibonacci numbers. Physicists Doddy and Konder confirmed with these experiments, dropping magnetic fluid into the oil under magnetic field. The droplets form spirals at golden angle just like sunflowers. Their model shows simple physics, repulsion, timing, and growth can lead to complex, beautiful, and mathematically precise patterns. Genetics sets the stage, but dynamics write the script. So next time when you see a daisy and sunflower, remember, nature isn't just beautiful, it's mathematically brilliant.
Now that is it for drops, dynamics, and daisies. We truly know that nature hides subtle beneath apparent chaos. Ian Stewart shows how simplicity emerges from complexity. From falling teardrops ending in singularity, and ecosystems dynamics where simple rules generate large-scale patterns, to daisies whose spiral arrangement follow the Fibonacci sequence through natural growth. We hope you learned a lot on our little blog. Thank you. Bye.